An electrocardiogram, or ECG, or the Dutch or German version of the word EKG, is a tool used to visualize the electricity that flows through the heart. An ECG tracing specifically shows how the depolarization wave moves during each heartbeat, which is a wave of positive charge. And the way it looks depends on the set of electrodes you're using. This particular set of electrodes is called lead 2, for example, with one electrode on the right arm and the other on the left leg. So essentially, when the wave's moving toward the left leg electrode, you get a positive deflection, like this big positive deflection corresponding to the wave moving down into the left and right ventricles. To understand the basics, let's start with an example of how we can look at the heart with only one pair of electrodes, a positive one and a negative one. Remember that at rest, cells are negatively charged relative to the slightly positive outside environment. And when they depolarize, the cells become positively charged, leaving a slightly negative charge in the outside environment. So let's say that when this set of cells is at rest, they're red. And then they turn green as the wave of depolarization moves through them. Now, if we freeze this wave of depolarization as it's moving through the cells, half of the cells are positive or depolarized, and half are negative or resting. And so there's a difference of charge across this set of cells. You can think of the charge difference as being a dipole, because there are two electric poles. And we can draw this dipole out as an arrow or vector pointing towards the positive charge. And remember, the electrodes detect charge on the outside of the cell. So this points toward where the positive charge is outside the cell. Now, if there's a dipole vector pointing toward the positive electrode, then the ECG tracing shows it as a positive deflection. The bigger the dipole, the bigger the deflection. If we unpause this, then everything becomes depolarized. And since there's no difference in charge now, there's no dipole, and so there's no deflection. Moments later, a wave of repolarization goes through. Pausing halfway through again, now the vector dipole goes in the opposite direction and faces the negative electrode, which means there'll be a negative deflection on the ECG tracing. Again, the bigger the dipole, the bigger the negative deflection. Now, even though it'd be nice if the depolarization wave lined up perfectly with the electrodes, usually that's not the case. So what we end up looking at is the vector component that's parallel to the electrode. For example, let's say the depolarization happened this way, at an angle. Then we'd break the vector into two parts, one going parallel with the electrodes and one going perpendicular. The one we care about is the one that's going toward the positive electrode, which causes the deflection. Though since this arrow is shorter, it's going to cause a slightly smaller deflection than previously. In other words, the size of the deflection on the ECG tracing always corresponds to the magnitude or size of the dipole in the direction of the electrode. The perpendicular component isn't pointing at the electrodes, so it doesn't cause any deflection. In fact, if there's a depolarization wave that goes straight up, which is perpendicular to the positive and negative electrodes, then there'd be no deflection at all.